Welcome back, mathematicians. We are now retracing our steps, head back to chapter 4 for just one section, and that section is 4.8, all about antiderivatives. We just spent a few weeks talking about derivatives and estimating derivatives and what we can use derivative for, related rate, optimization, and stuff like that. But there's lots of different problems that require us to recover the function from its derivative, right? So like I give you acceleration and a few other things, we can work our way back and find position and velocity as well. All right, so we define antiderivative to be like if a function f is an antiderivative of little f on an interval I, if big F prime equals little f of x. So that capital F is the antiderivative and little f is our like original function, all right? So the process of recovering big F of x from its derivative little f of x is called antidifferentiation. Similar to when we took the derivative, that was called differentiation. It's very common to make the antiderivative the capital letter. I like to make this little family tree. So if I have little f or little g or little h or even lowercase theta, its antiderivative is going to be the uppercase version of that. So capital F, or we say big F, big G, big H. Lowercase and uppercase take too long to say, so we say little f or big F. So I like this little, I call this the family tree of functions. So we have big F, I like to think of it as like the grandfather. Then we have little f, and then we have little f prime. If I want to go down the family tree, I'm going to take the derivative. And if I want to go up the tree, I want to take the antiderivative, and we usually denote that with an integral. And we'll get to more about this next section. But this is kind of the family tree, all right? So when we are talking about antiderivatives, we want to recover our long-lost original function, and now we're looking at a derivative, and I need to find where it came from. So we're asked to find an antiderivative for the following functions. So let's go to black, there we go. If I'm given f of x equals 2x, I need to think whose derivative is 2x. Well, I know that if I have x squared, if I take its derivative, 2 will come down, I'm just left with 2x. So that means that big F of x will equal x squared. And then I can double check that by taking the derivative. Oh, I get 2x, perfect, that equals little f of x. The good thing about antiderivatives is I finally have a way to check my answer. When we were taking derivatives, I really didn't have a way to be like, is this the right derivative? Like, I'm using all these different differential rules, but I'm still not like 100% confident. The best thing about antiderivatives is now you have a way to check by using all the derivative rules that you guys are so mastered. All right, so cosine. Whose derivative is cosine? That's the question we're asking. Well, I know cosine's derivative is negative sine goes to negative cosine, and then cosine's derivative, negative cosine's derivative is sine, and then we complete that over again, right? Because sine and cosine have this cyclical derivative. So whose derivative is going to be cosine? It is sine of x. All right? So h of x, this is a little bit of a tricky one. I need to kind of think a little harder. 1 over x, I know that's just a derivative rule on its own. I know that that's the derivative of ln of x. Now I have 2e to the 2x. Well, I can remember that e to the u's derivative is e to the u times u prime, right? Oh, those aren't equal, arrow. Okay, so e to the u here, right here, is e to the 2x times 2. Well, that means that it's the derivative of e to the 2x. All right? We're going to learn more antiderivative rules, so these will become a lot easier. So is there more than one antiderivative for a given function? Because we were told to find an antiderivative, not the antiderivative. Remember that constants derivatives are just 0. So what if I had like sine x plus pi? If I took the derivative of that, I would still get cosine x plus 0, because pi is just a number. Same with if I added like 100. That derivative is still 0. So we have this nifty theorem. It says if big F is an antiderivative of little f on an interval I, then the most general antiderivative of little f on I is big F of x plus c, where c is some arbitrary constant. So we usually like to call this a constant of integration. We'll get to more about that in a few chapters. But I could have gone up here and just put like a big plus constant right there. This is really important. If I don't give you a way to find this plus c and I ask for an antiderivative, I need that plus c or your answer is wrong. Okay? So find an antiderivative. Let's do an example. Find an antiderivative of f of x equal to 3x squared that satisfies f of 1 equal to negative 1. So this is called an initial value problem. I'm given somebody's derivative and I'm given that function's initial value. Initial value doesn't always have to be at 0. It could be at just any point on the graph. Yum, coffee. Okay, so kind of like, so we know, so now we're looking for whose derivative is 3x squared. Well, that looks just like an ordinary power rule derivative of x cubed. Well, that theorem up there says that I need to add this constant, and because, because since the constant's derivative is 0, I kind of get like this family of functions that are the antiderivative of 3x squared. All right, and then we can narrow down that family to find the one and only that has this initial condition. All right, I'm gonna plug it in. So f of 1 equals 1 cubed plus c is just a constant equal to, what's it equal to? Negative 1. All right, so then this is just 1 plus c equal to negative 1. So c will equal negative 2. We can then conclude that big F of x is equal to x cubed minus 2. If we draw all these like different families of x cubed plus a constant, we kind of get something like, there's x cubed on its own, x cubed minus 1, x cubed minus 2, plus 1, plus 2, and so on, right? But we want the one that intersects 1, negative 1, which we're going to make that one. All right. So out of all these different functions, we wanted this last one in particular. I know it's a really bad drawing. Bear with me. All right. So I kind of mentioned this earlier, but just like we had all those differentiation rules, we also can work our way back to gain similar anti-differentiation rules. Oops. So a lot of these rules will look similar, but a little funky at the same time compared to their corresponding derivative rule. So the first one is, I like to call it reverse power rule. So if we have x to the n, its antiderivative is going to be 1 over, wait, no, spoiler alert. So I'm not going to subtract 1, because that's how I would take the derivative. I'm going to now add 1. Right, so we started at x to the n, and now we're at to the x n plus 1. Just like kind of up here, we were at x to the 2, and then we went x to the 3, or x cubed. All right, well, if I take the derivative of this, power rule says that my exponent needs to become a coefficient. Well, that would leave an n plus 1 out front. So I need to cancel out that n plus 1 and divide by n plus 1. So basically, I need to take my exponent, add 1, make that my new exponent, and then divide by that same number or multiply by the reciprocal, the same thing. And just like we said earlier, we need to always have our plus c. All right? And in this case, n does not equal -1. Remember, that's a special case where, right here, that's when n would equal -1. We'll get to that one in a little bit. Now we have our few trig functions. Here we go. So I know we had a lot of derivative rules that had u involved with them and chain rule. These are kind of what I call quick chain rule. And when we talk about antiderivatives, and the opposite of chain rule is what is called u substitution. That u kind of, I mentioned in earlier sections, is going to come back. We won't get to that until maybe tomorrow, maybe Thursday, because this comes out on Tuesday. It's one of my favorite antiderivative rules, but we're not doing that right now. We're going to be just using kind of this like quick fix to chain rule. So if I have sine of x, its antiderivative is going to be negative cosine, antiderivative of sine k of x is going to be negative cosine kx divided by that k because of chain rule plus c. All right. If I take the derivative of negative cosine kx divided by k, I'm going to get back to sine of kx because those k's are going to cancel out from chain rule. Right? So cosine, its antiderivative we saw earlier was sine kx divided by k plus c. Secant squared is the derivative. Secant squared of kx is going to be the derivative of tangent. So its antiderivative is tangent. Cosecant squared is the derivative of cotangent. The best way to know all the antiderivative rules is to really know the derivative rules. So secant x tangent x will give me secant of x, and now we just throw in a k, help ourselves out. And this is negative, oops, I forgot a negative with the cotangent. The co's get negative. Negative cosecant kx divided by k plus c. All right. Now we have some exponential ones. E to the kx, we kind of already talked about. That's going to be, since its derivative is e to the kx, we're still going to have e to the kx for its antiderivative divided by that k to counteract chain rule when I take the derivative. Right, because in chain rule I'm going to multiply by k, and antiderivatives I'm going to divide by that k. And this only works for k being a constant. All right, and then 1 over x we talked about, that is ln of x plus c, and obviously x can't equal 0. Now these crazy guys, I hope these look familiar, because those are our inverse trig derivatives. So 1 over the square root of k squared x squared, or kx, that quantity squared, that is going to be the derivative of sine inverse kx divided by k plus c. 1 plus k squared x squared is going to be the derivative of arctangent, or tangent inverse, however you like to say it, of kx divided by k. 1 over x, k squared x squared minus 1 is going to be the derivative of secant x kx over k plus c, and in this case kx is greater than 1. So those are all of our arc ones, and then if there's a negative in front of it, that'll give me arc cosine, arc cotangent, and arc cosecant, excuse me, that we saw earlier with the same derivatives. These are going to be harder to see when you're given derivative, because you're going to be like, whoa, what is that? It's going to be best, that's why it's really good to know all of the inverse trig derivatives, because it's easier to see. So now, I don't know why in the book they left a to the kx alone. It made me really sad. Its derivative, remember, we multiply by ln of a. And so the antiderivative, we're going to still keep a to the kx, just like we did with e to x. And now we're going to divide by ln of a. And also we're going to divide by k, just because that's what we've been doing. Plus a big C. All right? And a here does not equal 1. So those are our big table of antiderivative rules. Just like you had all of your derivative rules, I highly suggest creating a chart, like a little cheat sheet to do homework. Just so you're not having to flip back and be like, is this right, is this wrong, and so on. You just have that sheet with you. So let's do a few examples. So we're going to find the general antiderivative of each of the following functions, meaning I don't have an initial condition, so I'm just going to leave a plus c. All right? So we have x to the 5. So I'm going to scroll up and I'm going to use what I call reverse power rule, which is this top guy right here. So in this case, n is 5. So if I scroll down, that means that big F of x will equal x to the 5 plus 1 over 5 plus 1 plus a c, a constant, which equals x to the 6th divided by 6 plus c. And if you want to double check yourself, we can take the derivative of that. And I get 6 divided by 6, x to the 5 plus 0, which is just x to the 5th. So we're good. All right. Now we have h of x equal to sine of 2x. So I go back up here, sine of kx. So k is just 2 right here. I'm going to have negative cosine kx divided by k. So means big H of x is going to equal negative cosine 2x divided by 2 plus c. And if I want to check my answer, I'm going to get negative cosine's derivative is sine of 2x divided by 2, 'cause that's constant, times the derivative of 2x, chain rule, plus the derivative of a constant is 0. So those 2's cancel out, which is why we divided by k in the first place. And we're left with sine of 2x, which is little h, which is perfect. It means our antiderivative is correct. All right, so then e to the negative 3x. So let's go look at our derivative rule. So I'm still going to have e to the negative 3x, and I'm just going to divide it by negative 3. And I'm going to add my constant c. Boom. If you guys want to check that one on yourself, you can take the derivative, and you'll see that big F's derivative is little f, which is, by definition, an antiderivative. So we also have some other fun little antiderivative rules. These are really similar to derivative rules, and also really similar to the Riemann sum rules that we talked about yesterday in sections 5.1 and 5.2. And Riemann sums, and I think when we talked about sigma notation as well. So, coefficient rule, if I have k times a function, its antiderivative is going to be k, that same constant, times the antiderivative plus a big C. The reason that k is only multiplied by big F of x and not the constant is because k is a constant and c is a constant, and if I multiply these guys together, I can think of this as like k times some other constant c1. Constant times a constant is still another constant. So I kind of don't even need that. Similar, if that k is a negative 1, I'll get that the antiderivative of negative little f of x is negative big F of x, still plus c. Even if that's if c is a negative number, it's still plus a constant. A negative number is still a constant number. Sum and difference. So if I have f of x plus little f of x plus or minus little g of x, I'll have big F of x plus or minus g of x, plus I would have a constant from f and a constant from g. Well, I can just combine those into being a super constant, and I can just call that c again. So we just call that, there we go, plus c. So if I multiply my c by another different constant, it's still a constant, so it kind of like a sponge, it's going to absorb if I multiply it by a constant, if I multiply it by a negative, and if I add another constant to it. You kind of just like beat it up, all right? So now we're going to find the general antiderivative for f of x equal to these two functions together. We can do a little example, all right? So let's rewrite little f of x so that taking the antiderivative will be a little easier. So 3 divided by the square root of x, 3 divided by the square root of x is, I can write that as 3 times x to the negative 1/2 plus sine of 2x. All right, so that means that big F of x, that 3 is just going to stay there because of this rule up here. And then I'm going to take negative 1/2 plus 1 divided by negative 1/2 plus 1. And then we actually already did the derivative, antiderivative of sine of 2x. Let's scroll up and find that. It was negative cosine 2x divided by 2 plus c. So we can erase that plus, make it a negative cosine 2x divided by 2 plus c. So now let's simplify a little bit. So negative 1/2 plus 1 That's going to be x to the 1/2 divided by 1/2 minus cosine, 2x divided by 2 plus c. And then we need to simplify. So this is kind of what I was saying by multiplying by the reciprocal is really useful. Reciprocal just means I flip the fraction upside down. That's how dividing by fractions works. So this dividing by 1/2 is going to turn into a multiply by 2. So I'll have 3 times 2 x to the 1/2 minus cosine 2x over 2 plus c. Simplify one more time. I'll make that a 6. We'll turn that into a square root. And we're done. So basically, I did calculus right here. And the rest of the way, I did some algebra just to clean up my function. Alrighty. And we're done. You can also take the derivative and make sure that we get back to where we started. And you would. Alright. So I kind of mentioned this earlier about being able to recover functions from their derivatives. So we were able to find velocity and acceleration from taking the derivatives of position, right? S of t was position. So now if we're given acceleration, we can, and a few initial values of s of t and v of t, velocity, we can get all the way back to position, the entire position function, all right? So if you tell me at one time the velocity and the position of something, then, and its acceleration, I can give you all of this information. So an example that's in your book is that a hot air balloon is ascending, so going up, at a rate of 12 feet per second, which is a velocity, at a height of 80 feet above the ground when a package is dropped. How long does it take the package to reach the ground given the acceleration of gravity is 32 feet squared per second? So that's an acceleration. Oopsies. And not feet squared per second. Feet per second squared. There we go. All right, and we're going to assume that there's no other factors on the package, like air, friction, whatever. All right, so we can write that our a of t, which is also the derivative of velocity with respect to t, is 32. But remember, the package is falling down towards the ground, so it's going to be a negative 32 feet per second squared. Okay? So just like we did with our first initial value problem, I'm going to find the antiderivative, and then I'm going to plug in my initial value. So if the derivative is a constant, the antiderivative is going to be negative 32 times a variable, right? You kind of have to, constants, antiderivatives aren't zero. They have to come from somewhere. Remember, coefficient, it comes to the party with somebody. Even if their variable leaves, they're still hanging out at the party. So we're kind of tracing back in time. That guy, he's still here, so we had to have accidentally turned on Siri. All right, and then don't forget plus our constant. And we're given a, let's say that right when the package dropped, that's time 0. So we'll say that velocity at 0 is, it's going to be 12, because the package is still actually going to go up a little bit when it's dropped, which sounds weird, but that's just physics. And our position at time 0 is 80. So now we're going to plug in our initial condition. Define C. Right? So V of 0 is going to equal negative 32. Not T. T is now 0. Plus C equals 12. All right. Well, that's just 0 plus C equals 12, and C equals 12. So now velocity, which is the derivative of position, equals negative 32t plus 12. Okay, and now we're going to do it again. So we're going to find the antiderivative. So negative 32t. T is kind of raised to the first power, so I'm going to have negative 32 t squared divided by 2 plus our constant now becomes a coefficient plus c. And now we're going to plug in our initial condition. So that s of 0 equals negative 32 divided by 2 is 16. So negative 16, 0 squared plus 12, 0 plus c equals our initial condition. Initial condition for position was 80 feet above the ground. So these guys are all zeros, plus 0 plus our constant equals 80. So then C equals 80. So I know I'm using C to be this guy right here and this guy right here. It's kind of, they're not the same C, right? This is still 12 right here. What I mean when I'm doing the plus C is that it's just a constant. Don't think that it's equal to all constants. If I wanted to, I could call this like C1. And this could be C2. Okay? So now I have S of t. And it's going to be negative 16t squared plus 12t plus 80. Right? Cool. So now I have my position function. Awesome. Well, let's go back and look at the question. And it didn't ask, I don't think, for just the position equation. We were asked how long, or lang as I wrote it, does it take the package to reach the ground? So we want to find the time when our position is 0. We usually call the ground 0, okay? So we're gonna let negative 16 t squared plus 12t plus 80 equals 0. All right, so each one of these things is divisible by 4, so I can pull 4 out. That's going to be negative 4t squared, just makes our life a little bit easier, plus 20 equals 0. And then I divide by 4. And we'll get negative 4t squared plus 3t plus 20 equals 0. I don't think we can factor that. I also hate factoring when there's a number in front of t squared or x squared. So I like to use a quadratic formula. If you don't know the quadratic formula, I'm going to sing it to you, but you should know it by heart. All right. So we're going to have that t equals negative b, so negative 3, plus or minus negative b plus or minus the square root of b squared minus 4ac da 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 all over 2a, which is negative 8. Great. Really hope my Algebra 1 teacher is very proud of me. Okay, cool. So that's going to simplify to negative 3 plus or minus the square root of 329. I didn't just do that in my head. I have all these answers already. Cool. So quadratic formula gives us two answers, so that t is either negative 1.89 or t is approximately 2.64. So remember that the package is dropped at time 0, so I don't think we can choose a negative time. That has no physical meaning. So we can say that the package hits the ground at 2.64, don't forget your units, seconds, all right? That is the ugliest 4 I have ever seen. Okay. Beautiful. All right, cool. So here's the kind of the integral that I was talking about. All right, so we defined that the collection of all antiderivatives of f is called the indefinite integral of f with respect to x and is denoted by this symbol. It is not an s. Do not draw an s. It's not an s. It is an integral. It is its own object. Okay? We say integral of f of x dx. This dx is really important. Well, so is the integral. So I kind of like to think about these as a sentence, right? You start a sentence with a capital letter. Think of that as the integral right there. And you have to end it with a dx. This is that dx. If you don't have that dx there, your answer's wrong. I'm sorry. It just is. It tells me kind of like when we divided by like dy dx, df dx, it tells me what I'm integrating with respect to. All right, it tells me what my variable is. It's also like the period in a sentence. If I don't have it, I don't know what's included in my integral and what's not. That's why you oftentimes, if you look down here, we'll see like kind of like a parenthesis so that we know that dx is on to each one of these terms. All right, so the symbol swirly Q right here is the integral sign. The function f is called the integrand. It's the kind of the inside of the integral. And x is the variable integration. And we'll talk about the variable of integration a little bit more. So, I was about to write something, but we'll get to that later on. Now I can ask you to evaluate each of these integrals. Also, I think integrals are like the most beautiful symbol ever. Cool. So we kind of already did some of these earlier. So, right, the integral of 2x dx, well, we know its antiderivative is x squared, but remember, it's the collection of all of them. What does that mean? That means that I need to have, I was looking for those close by, a plus c. Okay? If I have e to the negative 3x, well, we talked about that that was e to the negative 3x divided by negative 3. I'm having flashbacks. I think I just divided by 3 and I'm freaking out. It's fine. But that's not it. I need to plus c, right? Because c could be anything. That's why it's a collection of all of them. It's like a little family. All right, and now we have this one. Sum and difference rule says I can split them up. So I can do that. That also means that the dx can go to each one of them, which is also good. If it was just on that 5, I literally don't know what I would do. So I can write this as the integral of x squared dx plus the integral of 2x dx plus the integral of 5 dx. And now I can work on them just like I did with derivatives, one term at a time. All right, so let's pull out any constant, or sorry, not constants, coefficients, plus 2 integral of x dx plus, we can pull out a 5 here and just leave that as 1. Sometimes that helps people see that because x's derivative is just 1. All right, so let's keep going. This is going to be, actually going to write this over here. It's going to get pretty long. X cubed divided by 3 plus c1 plus 2 times x squared divided by 2 ooh, there's a minus somewhere. Minus, 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 plus, let's do that, c2 plus 5x plus c3. Well, then that'll come out to be x cubed divided by 3 plus c1 minus, those 2's are going to cancel out, so just x squared minus 2c2 plus 5x plus 5c3. The reason I'm not just collecting all of these c's right yet is because I want to show you how we can call big C c1 minus 2c2 plus 5c3. So I'm collecting all of my constants that came from each individual integral above, and I can just make it one big C. Plus my constant. And we're done. So it is kind of good practice to add your plus C on each one of them and kind of understand that this plus C is the combination of all of them. But once you get more of a hang of it, it's just you simplify and then add plus C. Alrighty, so that's it for 4.8 and learning all our antiderivative rules. Next section is going to be 5.3, and we're going to kind of learn a little bit more about if my integral now has some bounds on it and what that's called. All right, I'll see you guys there.